All right, let's dive into a subject that's been moving out of the shadows and into the spotlight of serious scientific research: unidentified anomalous phenomena, or UAPs. Today, we're not talking about theories or speculation. We're going to look at the actual science, how researchers are using some seriously advanced tech to figure out what's really happening in our skies, and maybe even beyond. So this is the million-dollar question, isn't it? It's the one thing driving this entire revolution. We're so past the point of blurry photos and grainy videos. The real challenge is about a rigorous, data-driven process. How do you scientifically prove that what you've detected isn't a satellite, isn't a weather balloon, isn't some weird reflection? How do you isolate a true anomaly? That's what we're going to break down. Okay, first things first, let's get the terminology right. You're going to hear me say UAP, not UFO. And this isn't just about being politically correct. It's a really crucial shift. UAP, unidentified anomalous phenomenon, is the official term for a reason. It widens the net beyond just flying objects to include anything strange, whether it's in the air, in outer space, or even deep underwater. It grounds the entire conversation in science, which is exactly where it needs to be. This really is a whole new age of detection. The entire game has changed. For decades, it was all about stories, right? Eyewitness accounts. But now we're moving away from anecdotes and toward creating hard, verifiable data. The mission is to turn these fleeting, mysterious moments into something permanent that we can actually analyze. And this right here gets to the absolute core of the issue. Look, people have been seeing weird stuff in the sky forever. The problem has never, ever been a shortage of sightings. The real challenge, the one that scientists are tackling head-on right now, is a data quality problem. They need high-quality, corroborating evidence. That means multiple, different sensors all picking up the same thing at the exact same time. That's how you build a case. So how do you solve that data quality problem? Well, you need the right tools. And we are talking about a seriously high-tech toolkit. Think of it as a multi-layered arsenal of sensors, where each one is designed to capture a completely different piece of the puzzle. So let's open up the toolbox and see what's inside. The first layer is probably what you'd expect: visual sensors, stuff that can see. We're talking about way more than just a fancy camera. Sure, you have high-resolution cameras, but the real star of the show is infrared, or IR. These cameras don't see light, they see heat. And that is absolutely crucial because it can detect objects that are totally invisible to the naked eye, or things that give off a really strange heat signature. It's a whole other layer of reality we can now record. And then we get to the really cool stuff, the sensors that detect the invisible. You've got advanced radar, tracking an object's speed, its altitude, its trajectory, with just mind-boggling precision. You have radio frequency scanners that are basically listening for any weird signals. And you even have magnetometers, which can pick up bizarre shifts in the Earth's magnetic field, a signature that gets reported a lot in these encounters. It's all about painting a complete picture of an event, not just what it looked like. Okay, so you have all this incredible data pouring in. What do you do with it? Well, before anything gets the UAP label, it has to go through this super rigorous process of elimination. You start with the basics, document everything: time, place, weather. Then you pull in all the evidence from every sensor. But step 3 is the most important part: cross-referencing. You check everything: commercial flight paths, military training exercises, satellite orbits, weather balloons, you name it. Only after you've ruled out every single known possibility can you start to think you might have something truly anomalous. But here's the catch. This high-tech toolkit creates a new problem: an unbelievable, overwhelming flood of data. It's way, way too much for any team of humans to sort through. You need a way to find that one tiny signal in an ocean of noise. And that's where the AI-powered analyst comes in. I mean, seriously, try to picture it. You have cameras watching the sky 24/7. You have radar systems constantly sweeping. You have endless streams of data from all those other sensors. We are talking about petabytes of information. That's a mind-boggling amount. And hidden somewhere in that digital ocean might be just a few seconds of something truly extraordinary. How in the world do you find it? Well, the answer is you train an AI to find it for you. And we're not talking about simple software. These are incredibly sophisticated algorithms, partly inspired by the same kind of tech that physicists use to search for the faint signals of dark matter in giant particle colliders. It's about teaching a machine what normal looks like, so it can instantly flag anything that breaks the rules, like, say, an object that makes a sudden right-angle turn while moving at Mach 2. So what does this AI actually do all day? Well, it's constantly working to filter out the boring stuff. Birds, planes, lens flares, you name it. It's designed to spot subtle patterns across all the different data streams that a human analyst would almost certainly miss. It can even go through infrared video, pixel by pixel, looking for changes in heat that show an object moving in a way that just defies physics. This AI is, and I'm not exaggerating, an absolute game changer. Now, this amazing technology isn't just being used in some secret government lab somewhere. What's really starting to happen is the creation of a global watch network, and it's bringing together two very different groups: the official, government-led projects and a fast-growing movement of citizen scientists who are building their own monitoring stations. You've basically got these two fronts working in parallel, which is fascinating. On one side, you have the official government effort, the Pentagon's AARO office, which investigates reports from military pilots and uses top-tier sensors. And on the other side, you have these incredible open-source projects like SkyHub, where regular people are connecting their own sensor arrays to create this huge, public, global database. Both are adding crucial pieces to the puzzle. Now, of course, each approach has its own strengths and weaknesses. Setting up multi-sensor stations in the field gives you incredibly rich, robust data. But man, it is expensive and complicated. Using satellite imagery gives you massive coverage of the planet, but you might miss something if the satellite isn't looking at the right spot at the right time. And crowdsourced data gives you a ton of reports, but it's much more likely to include misidentifications. The real magic happens when you start integrating all three. So if you were to give a kind of report card on where things stand today, it would look something like this. The tech is doing great. Our sensor coverage gets a solid 8, and the AI integration is a rock star at a 9. The area with the most room to grow, you see, is community contribution. The potential is huge, but there's still work to do on making sure all that citizen data is standardized and verified so it can really have a major impact. And the search isn't just stopping at the atmosphere anymore. The new frontier is what's being called multi-domain detection. It's this recognition that whatever these phenomena are, they might not be limited to just the sky. That's right. Investigators are now actively looking for unidentified submerged objects, or USOs. This is a direct response to some very credible reports, many from the Navy, of objects that seem to move seamlessly from the air into the ocean and back out again. And to do that, they're using tools like active sonar and super-sensitive underwater microphones called hydrophones to listen for anomalies in the deep. This quote right here, I think it just sums up the whole effort perfectly. This isn't really about finding aliens. It's about the scientific process itself. It's about systematically collecting good, clean data on things we currently can't explain, and then using that data to push the boundaries of what we know about physics, about our world, about everything. So, if you take just one thing away from all this, let it be this. The study of UAPs has graduated. It has left the world of sci-fi conventions and has firmly planted its flag in the world of serious, data-driven science. This is a sophisticated, multi-domain discipline that's using some of the most advanced tech we have. When you step back and look at it, we've really reached a fascinating point. The cameras are rolling, the sensors are listening, and the AI is watching the skies 24/7. For the very first time in history, we have actually built a systematic scientific machine designed to hunt for the unknown. We've built the tools to see the unseen. The only question left is, what will they show us?